So I think what I really would like to do at the end of this sort of lesson is get you sort of experiencing doing like some sort of modeling and actually solving the model. And we'll solve a model numerically on the board, which is quite sounds crazy, but it's doable, I think. Okay, so yeah, we can't cover everything. I mean, I can't teach you everything about modeling, everything about differential equations, everything about DCM as well. But I want you to get a good background. So if you can go ask questions, or if you want to use this or critique this, you know the ins and outs of this. So before reading this article, how many of you were interested or heard about DCM? So that's quite hard. So people sort of understand, yeah. People kind of have seen it before. Does anyone think they know what DCM is? And want to volunteer to explain what DCM is? No? You should never ask the volunteer, you should just pick people. The first lesson, I think. I think so, the way I see DCM is kind of like this. So in the past, or many neuroimaging studies, you kind of do a task. So this here, I'm showing a task where someone's watching something in the visual field in an MRI, and they're asked to do an attention task, like attend left, attend right, throughout the entire sort of paradigm. And so you do this, record it, and you find activation sites. And if you do an attention task in visual domain, you'll find activations in V1, V2, and because you have attention, you have things like in the parietal regions, like IPS, or that kind of fun stuff, as well as like the attention networks, like the dorsolateral frontal cortex. And then historically, you'd have this task, you'd have these activations, and then you'd be like, okay, I'm going to explain these results in a discussion. So I'm going to draw the following diagram. I'm going to say, okay, I'm going to have, you know, V1, V2, I'm going to have IPS, and I'm going to have dorsolateral frontal cortex. I'm going to draw these boxes, like these sort of wiring diagrams do. And I'm going to have an input for all these, something like, I call it U. So you have an input due to the visual stimulus, which will go directly into V1. And then you'll have connections that go to V1 to V2. You have this sort of visual pathway in dorsal stream and so forth. You have also these sort of diagrams here. And then you also have additional type of connections. Because you have an attention task, you're going to affect directly the attention network. This kind of these sort of modifiers. Well, this can be some sort of an abstraction of how it kind of reaches these attention networks. And this is normally done, and then they would say, okay, well then due to previous studies and just due to our kind of analysis, all these are engaging this sort of this task. We hypothesize these links because we've seen these in monkey data, in rat data, et cetera, et cetera. And there'll be a paragraph on it, and that's it, the paper's done. So the way I see DCM is a process of changing that paragraph into something testable, quantifiable. Because you can say easily here, I mean, how strong is the connection from there to there? Is V2 going directly to, is there a connection there? Is attention in these high order networks, are they going backwards, back to V1? So DCM can find a framework which formalizes all these questions. You can have a range of, I don't know, 10 different models, and also you have different wiring diagrams. And DCM provides the machinery to actually answer these questions. Given our data, which model has the best evidence for this? So which model can predict these responses in ball activity? Because I've drawn these here, but they're all, you know, there's a V1 response and a V2 response. There are all these kind of responses. So it tries to fit all these responses given this model. Good, coming right in time. Good. I've just gone through the bit of the background what DCM generally is.
Hang on, I'll grab another chair.
Okay, so this is essentially what DCM is. Does anyone have any problems, any questions here? No, it seems okay. Please ask. Don't let me just sit here and do all the work. Okay, now the way to do all these tests, DCM has this sort of big machinery, and it goes in two different stages. So the first thing it has is what's called sort of a generative model. Okay, so you might have seen that in the paper or people talking about DCM. Then you have another part of DCM. I'm making this split here. Model selection and inversion. Okay, so basically that formalization which I talked about before, this is how it's set up. So the generative model, what it does, it takes all these wiring networks and it applies a neural model. So you have these neural models which can relate the activity of all these structures together. So they call them hidden variables. That's part of the generative model. The reason why they're called hidden isn't because it's something spooky, it's just because you don't measure this in your experiment. They're hidden by design. And after these hidden variables that are in place in all these things activating, so they're all in this sort of neural domain, they then are used in an observation model. Should make more space here. And yeah, I'll call them now observable variables. So in generative model, you have something that produces these responses, then you apply this observation model, which gives you actual ball time series. Then you use that to fit your data. You want to then vary parameters. So in each of these models, there's parameter connection strengths. And in this section, what it does, it tries to find the best fit. So it changes each of the parameters in a systematic way. And so also one of the big criticisms of DCM is that it can change anything. If you have more and more parameters, you can fit anything. But what DCM does, which is the response to that, is that it uses prior information. So you have prior information to constrain your models. So you find the best model given a wiring diagram. And then what you do is you have another wiring diagram, and you have all your wiring diagrams you have. You've got to make sure you have all of them. And then in this section, it picks the best one. And this is more, I guess, what DCM actually is, these two components there. So this section here on model selection and inversion is all in a Bayesian framework, and we won't talk about this today. This will be kind of lecture 2 and 4. And today I want to talk about this section here, the generative model. So in terms of how to generate these hidden variables, what are the processes in there, what kind of maps do you need to understand what's going on. And I'll also go through observable variables probably next week. Okay, sounds all good. Please stop me if anything doesn't make sense here.
How do you define priors?
Oh, that's a good question.
And what are priors? Like what parameters would be the priors?
So for example, things you can have is, let's just say we have an observable variable. So you have the neural activity Z, and that gives you a ball time series equal to Y. So in this, there's a hemodynamic model in there. And in that hemodynamic model, you have things such as the signal decay rate of the responsive arteries. You have things such as the oxygen extraction fraction, rho, and so on and so on. And so you would have prior information, prior beliefs of this due to independent recordings. You have, for example, invasive recordings of how the vessels react and all that kind of stuff. And then you would form a distribution. You would say the mean value is here of kappa, and you have a distribution. And so when you do all these kind of model selection and inversion, you kind of so this is here is likelihood. So P kappa, we'll call it. So you expect it to be around the mean, but if it's least and least likely, the further away you get from the mean. And this is all taken into account in this section here. Because if it's very, if it's not that likely, you have to penalize that. So there's a lot of punishment in this here. You penalize these factors there. You also penalize model complexity. If the model's too complex, you're going to say, okay, it's too complex, so this should be weighted against you when you select the winning model. Yeah. Any more questions about that? Okay, this is very, very generic. So we're going to go into what this is here. Check this out. I cleaned it earlier. Okay, so now in the paper, you'll notice on figure 2, there is a crazy amount of maths in there. And you have sort of all these wiring diagrams, you have the bilinear model. Should be on page 1279, there we go, perfect. And who's scared off by this? If you're scared, tell me right now. Yes.
Scared.
Yeah, I think there's too much stuff in there, and I'm just on a rant. I hate having equations in figures all the time. I having too many of them and not reference anywhere else. So yeah. Anyway, that's my rant over. Okay, so
You tweeted that.
I tweeted that.
That's what that was.
It's okay if they're in there later and referenced later, but in some cases, I mean, Bristol papers, they're not even. Anyway, okay, so what does this all mean? So I'm going to draw this in a much more simpler way. So what you have your inputs. The input here, and for this next one, modifier. So it's like a conditional modifier. Okay, so these are kind of your inputs at the start. This is what you give into to DCM when you do this generative model. You then have these connections which go to a region. Okay, it's like region 1 was region 2. I've drawn a couple more regions of what they do in the paper, but that's okay. Not just region 4. Okay, so each of these regions here is all the neural activity. This is what they call the hidden variables. That's what all these regions have. And they call them Z, but we won't write that on this, so it's a bit confusing for now. And so each of these connections here, they have these type of things there. They're embedded in the bilinear model. They're called, I think they're called A's. They're like A, like the A terms. They have kind of the self connections between all the different regions. Okay, that's exactly how it looks like in DCM. And then what you have at the end of this, you have your observation model. Y1, Y2, Y4, Y3. Now the reason why I've drawn this in blue is because they all have their own little observation models. Okay, they're all governed by something that you want to measure. So, for instance, in bold, you have a hemodynamic model in each of these, and each of these have different parameters in them. So, as I said before, as Arina asked about the prior information, you have prior information on the decay rates of the vessels. So, when you actually fit data, what's nice about this is if you have hemodynamic variability. So as you know, typical measurements, you find different hemodynamic responses here, here, and here, and here. This can capture it as well. We'll try to fit by varying them as well on each of them. And this is the generative model. So this here is essentially what's in spectral DCM. You have all these connections going to one another, and you have these observation models. What's not in cross-spectral DCM is these other terms, these modified terms. They call them U2 in that figure. So what are they? Okay, what they are, they also directly go towards the regions, maybe not there or not, and they are something like an attention task or whatnot. So they can influence these directly, and that's what this part of the model framework is. So again, this part you don't need for cross-spectral DCM, but it's needed for task-based DCM and stochastic, the generic DCM. So I said also that these Y terms, they are for the hemodynamic responses, but it can also be MEG responses, EEG. And DCM now covers EEG, fMRI, MEG, and ECOG as well. and all these sort of observation models. They can be quite complex too. Just drawing white would be quite complex. Okay, this is what we're going to build towards the next two goes and how to actually interpret this. So now you'll see in what is equation number? Equation 1, the first equation in the entire. Everyone got this down. So, does anyone know what that is? What it's called? It's like Z equals F. It's Z, U. Anyone want to guess what this type of equation is?
Function.
That's a function, correct? This can be nonlinear, so it can be like just a straight line, it can be Gaussian, all that kind of stuff. But what's this entire thing, this class of?
Differential.
Yes. So this is a differential equation. Okay, so it's normally written like this.
That's the extent of it.
Okay, yeah, that's the extent of it. So this is a differential equation. So this here is the heart of DCM in terms of that wiring diagram is all fed through an equation like this here. And the connections you put in affect what this functional form is, and so on and so forth. And this is a very generic way to describe neural activity. It's very, very generic. This function can be hideously complex. It can be very, very complicated. It can be highly nonlinear. You can have some stochastic variation in there as well. So it can include like people like dB, to include noise, all this kind of stuff. So we're going to make this equation less scary. This is what we're going to do today. It's already scary. Alright. So I'm gonna now wipe it off to remove your horror. But we're going to get to this equation, and you can see in figure 2, this equation isn't there. So if you turn to figure 2, that bilinear model, so it's not equation 2, this one here. So that big equation to bilinear model does not look like this. It's much more, I guess, doesn't have an F term, it has all linear components and sums and things. So we're going to show you why that's okay for DCM. Okay, so differential equations. Alright, now, all differential equations are most things in physics and in dynamics and sort of mathematical modeling. A lot of these things all have differential equations. So you always have a rate, you have a variable v, for instance, and you have a rate term. And that equals something. Now the reason why we always deal in these rate terms is because a lot of things are measured in terms of rates. And when you think about in physics, for instance, if you have, so I went through this in our brain meeting, but I'm going to go through it slowly today. So sum of all forces, this is Newton's laws. This is actually a rate. This is the second rate, we can also call dB, dt. So these rate terms. So when you talk about things also like population, so if you talk about population over time, you normally say, for instance, a population is doing something over time. Or if you look at, I'll make this time maybe years, and population, you'll say the rate of population is decreasing, for instance, or it's always on dp dt. The rate of this is always negative. Another way you can say it is if you have population over time. So another way to represent this is in this space, not the rate, but in this space, you see decreases over time. So you normally have things represented in these rate terms, which is why everything's in rates. Other things you can have also the rate of consumption, for instance, rate of fuel. So one thing that's known very generally is that it's proportional to how fast you're going. Things like that. So this is another kind of rate equation. And this turns into a differential equation. You have f dt equals some constant, we'll call that k, times v. This kind of analysis here. So we have a lot of these rate equations in many different scenarios. So this is why differential equations are used all the time. So I'll show you how to calculate a rate. Now, I'm going to rub all this out the top part anyway. So an example I showed in the brain meeting, and I'll show again, is velocity. So if you were to look at distance x, let's say you're moving somewhere, and this is time t, let's say in 10 hours, you go from here, from 0, and you go all the way in 10 hours, you walk all the way to, I don't know, what's 10 hours away? Sydney.
Drive.
Let's say it's Stuart's house. So you can say, this is here. Now the rate of us walking to Stuart's house, you would say it's, calculate the change in x, yeah, and divide by change in t. So you would say this will give you the speed of walking. So this is the rate. Now if you go at a different speed, instead of going constant, if you were to do this instead, and if you calculate this as well, you see this gives you the answer. Let's say it's, let's pretend your house is 100 kilometers away. That equals 10 kilometers per hour. It's pretty fast walking, isn't it? Maybe cycling. Okay, but if you calculate it here, of course you're changing your speed, right? You're getting faster and faster, you get different speeds. So what you have to do instead is to kind of bin it up here, and in this small little time period, you can calculate it again. Do you ever understand this? Sort of? No? And if you were to plot this now, what the actual speed is as a function of time. Okay. So I'm going to do this for every point in time, and what you'll see is that if I can do that, it's actually a straight line. Okay. So I've calculated this at each point, and what this turns into, instead of, we won't call it dx dt like this. It's not this. What it actually is. It's this continuous form, dx dt. Because if I make this tinier and tinier, I get to a limit and approach it like a straight line. Okay, this is the starting point. So if this doesn't make sense at all, please stop me right now. No? Yeah? Nigel? All right. Alex, when you're watching, press stop and come to my office. Okay. All right. That's the starting point. This is why you need a rate. All right. Now we're going to solve an actual problem. That's to do with rats. All right. So we're going to solve the first problem, rat death. Okay. So now we can have a differential equation. We can start off. We can say rats are dying, right? So rats equals y. I'm going to call it y, variable y. And we find that the rate of change of rats dying equals, there's 10 less rats per unit of time. Oh, sorry. So we'll take a unit of time, now say that's rats per hour. So this says there are minus 10 less rats per every hour. This is what we start off with. So this here is a differential equation. We're going to solve it. All right? You ready? Okay. So how are we going to solve it? So there are many different ways to solve differential equations. I mean, this is a very, very long history, like hundreds of years. You can solve them analytically by doing all these crazy fancy maths, or you can solve them numerically, which is what we're going to do today. Both equations have their difficulties, and this is an example which I think you can all do at home, do at work, using like computational tools. So let's go how to start off this differential equation. The reason why I want you to see how this is solved, just to get a feeling of how these equations are, and then you can do your own modeling yourself and solve it yourself, which is quite hopefully quite encouraging. So dy dt, as I said before, it was like a continuous. We said before we had something like this. If you took small and small time points, for instance, it's a continuous version of that. I think it's small and small time points. But let's make an approximation. So for a very small segment of time, dy dt is approximately the changing y by the changing time. Yeah? This is okay? Okay, now what does this actually equal to? So what this actually is, so the time, at time ti plus 1, okay, you have a y value. Of course, you minus it at y of t of I. That's what delta y is. Okay so far? And the bottom part, delta t, is t of I plus 1 minus t of I. So exactly what we have here, but now formalizing this. Okay, now let's apply this approximation to this here. So if we say the following, if we say y of t of I plus 1 minus y of t of I, let's keep this fixed here. Okay, that equals minus 10. So I've just put this into this equation here. That's okay? Now let's go next step. If you take y of t of I plus 1 minus y of t of I, it's just algebra here, minus 10 delta t. If I get my algebra wrong, sing out. Get an extra point in the exam. Big measure exam. And then we can say y of t of I plus 1 equals, so I'm just moving this around, 10 delta t. And that's it. That's the equation we're going to get. So what we have here, we've taken a differential equation, we have a numerical approximation for the derivative, and we have a numerical implementation. Yeah? Okay. Now let's actually solve the problem. So let's draw this here. I'll keep this here for... So if you're a fan of rats, I'm sorry for offending you, I just have those rats.
Mosquitoes, no one's a fan of mosquitoes.
Mosquitoes. We can say mosquitoes instead. Okay, so we take 1, 2, 3, 4. Okay, so how do we solve this? Okay, we need some starting points, because as you can see here, it's telling you at a forward point in time, it depends on the previous point minus this delta t. So if we say at t equals 0, yeah, we'll say that there are initially, okay, so let's say mosquitoes. And people like rats, so let's make them mosquitoes. There are 100 mosquitoes. Yeah? Okay, now let's put that in. Y of, say t1, next time point, equals y of 0, that's the initial condition, minus 10 times delta t. Now we're going to assume that the difference in time, each of these time points, will make it equal to 1. We just said how small we want the approximation to be. So what does this equal to? Can someone work it out for me? 90. Alright, so 100. So we say at the first time point here, it is 90. What does y2 equal? What does yt2 equal to? So remember, this is the equation, which is y2 equals yt1 minus 10 times delta t. 70. Is it 70?
No, you still use the, if you use the original transport,
80, yeah. So the way we did that is we say y of t2 is equal to y of t1 minus 10 delta t. That's how we did that. So it's 80. Now you see a trend equal, what's 3? At 3 days, what does that equal to? So yt3. 70, yeah. As you can see here, it's fairly boring. I would say 4 it's 60. It's linear by design. Let's say we solved the differential equation. Yes! That's so hooray! So you've solved the first differential equation numerically on a whiteboard. On your piece of paper, actually, I should say. And so a lot of differential equations do this. Okay? When you have a very, very complicated equation, you do some approximations like this, and you solve it this way. And you can see here, if you were MATLAB savvy, you put it to a for loop, right? You'd say the next time point equals the previous time point minus 10 times that. Yeah? Okay, let's solve another harder one. So, just a heads up, what I'll be doing now is I'll show you this one, and then another one, and then we'll wrap it up. So I'm going to show the 2 extra cases that are very important in terms of most dynamics. Okay, so instead of saying they die at a constant rate, we're going to say it's dependent on its actual state. So the rate of change isn't a constant value, but it's state dependent. So we can say this. So this here is saying that the rate of change of mosquitoes is decreasing always of 10% of its current population. That's what it's saying there. Okay, this is the differential equation. So now we're going to solve this one in the same way. So again, dy dt equals dy over dt equals y of t plus 1 minus y ti divided by delta t. Yep. And I'll also add this, I didn't add this before, but this is essentially what's happening, that t is approximated this way. It's actually ti plus delta t. So this is how y advances, dy advances how t advances. Just let you know that's happening in the background. Okay, now let's put this into this equation here. So to do that, we have y of t I plus 1 minus y of ti divided by delta t. That equals minus 0.1 times y of ti. Is it okay so far? Yep. Now let's get this. Let's make ti plus 1 subject again. Y of ti plus 1. I'll do all the steps. Minus 0.1 y of ti times delta t. Keep on going down. If I do more rearrangement, you have y of ti plus 1 equals y of ti minus 0.1 y of ti delta t. So again, we have a numerical scheme. You can go ahead and put this into MATLAB, but this is kind of like essentially the older way to actually solve differential equations when you didn't have a computer and you couldn't solve it by brute force analytical mathematics was this way. So this is actually called the Euler method. This is how he solves some differential equations as well. Okay, so let's now start with the same initial conditions. Okay, at t equals 0, y is equal to 100. Yep. So let's work out what is t. Can someone work this out for me? T1 is equal to y of 0 minus 0.1 times y of 0 times t. What's that? 90. Okay, good. Okay, so I'm going to put this on here. Now, what's y2? T2?
81.
81. Good. So that's somewhere like here. What's y3?
71.9.
71.9. We'll make it 72. Approximations. What's 4? YT4? Use a calculator if you need to, don't be shy.
64.71.
64.71, let's make 65. That could be higher. Yeah. So now we've solved this equation. If you go on and go on further, what you'll notice here, what does it look like? So first off, rats are dying much more slowly if you have the state-dependent differential equation. And they're dying off kind of exponentially instead of linearly at this rate. So if you actually go through the maths, and if you actually were to calculate this yourself on the computer, if you have to measure this or calculate using that fitting exponential, you'll find out that this is the rate. It's actually 0.1. So we've solved this differential equation analytically now, using numerical methods now. So this here gives you, this is a very common thing you see in dynamical equations, is if you have a variable and you have its dependence in rate of time, if it's minus times its own dependence, so it's state dependence, but minus in this sense, you have a decay. This is a generic thing which can happen. We have other things kind of interacting when it gets more and more complicated, but you can say when this thing happens, you have a decay. This is the second class differential equations. All right, last one. This look okay to everyone? Is everyone confused? You can go and do this yourself on your computer. You can change these parameters and see how that changes. I think it's quite useful just to understand modeling and understand what DCM is actually doing. Because this is what DCM does. It has these models and just solves them in something like this. Okay, the last one, which you won't do calculations on because it will be a little bit harder. I'd love to show you the result. Is the following. Let's introduce, I was going to introduce a cat, and I can't introduce a cat anymore because it's got a mosquito. Let's introduce a frog. Frogs aren't getting eaten. So mosquitoes, let's just say mosquitoes, they normally have a mean population. That's mosquito mean. Okay? But we also find, we'll say mosquitoes and frogs. So we can say there's a stable population. That both mosquitoes and frogs live in harmony. But what we found, you can say, if you find fluctuations in this, we find when there are a lot of frogs, they actually eat the mosquitoes, and the surplus of frogs. Okay? And then you can say that in the surplus of frogs, they actually, we'll call this X, by the way, we'll call it X. So we'll say these variables describe the fluctuations above the mean. Okay? Just to tell you how much there are above or below the mean, above or below the mean. So what I've done here, I've had this approximation, is like the steady values. So you can even say in neurodynamics, you have the steady oscillations or the steady firing rate. And what you care about is like the perturbation on top of this steady firing rate. This is what we're doing here now, an approximation. Okay, now what we want to do is, we know this is pretty straightforward. We want to know the dynamics of these guys. So we now know the surplus, the ones above the mean, the dy dt. We know mosquitoes, I get an Eden, let's just say, minus x times 0.1. Okay, they get an Eden at a rate of 10%. There's 10% less of how many frogs there are. So 10% of the frogs are eating mosquitoes. Okay? And we can also say, if there are a lot of mosquitoes, of course, there's going to be a lot of food for frogs. Therefore, a lot of frogs are going to start to have babies and so forth. So depending on how many mosquitoes there are, there's going to be more. How many mosquitoes are above the mean, there's going to be more frogs. But of course, if this drops below negative, below the mean, you're going to have less surplus of frogs. Okay? So these are our differential equations now. Before we had just one, now we have two things, two populations. You can think of two neural dynamics, make them parallel to DCM, something like that, you know? And that one there is like negative. So it's exactly what it is, something like this, a coupled equation, and you have a positive contribution due to y, and you have a strictly negative contribution due to x always. Okay? Yep. Now let's solve this as well. Again, do the same thing again. If you make, hold on. Everyone got this? That's not easy. Let me just move this top. Again, I'm going to write this again because, so y of t I plus 1 minus y of t I divided delta t, and the x, the same thing. For the same sample of time, we have the same exact. Okay? Now we're going to substitute it into our equations again. So we're going to put this, y of t I plus 1 minus y of t I divided by delta t is equal to minus x of ti times 0.1. Yep. And then we can do the following, ti plus 1 equals, I'm going to skip all the mathematical equations, but it's steps equals this, minus delta t times x of ti 0.1. And that is our equation for how y varies. Now let's look at, this is the mosquito population, let's look at the frog population. So we have x of t I plus 1 minus x of t I. I'm going to put it to the equation which we had written down before. A equals y of ti. X of ti plus 1 equals x of ti. I went to skip some maps. If you're wondering where things are, it's because I skipped a step. But I can show you it's right. There we go. So now we have a numerical scheme as well for the frog population and for the mosquito population. So as I said before, this is done all the time. When you have numerical things in MATLAB, they do stuff like this. They might do a bit more fancy versions of this. So this step here might be a bit more fancy. I have more components if you want to make this approximation more accurate. But it's essentially this process. You put this approximation in, and you rearrange to get a forward step. Cool. Now, I was going to go through t equals 1, but it's going to take too long, so I'll just show you how it looks like. So who thinks they know what it's going to look like? Just on the model of what it is, frogs eating mosquitoes and mosquitoes getting eaten.
Oscillations.
Oscillations, yeah. So I think Manuel's getting there as well. But that's how it looks like here. That's my PowerPoint. Here we go. Yeah. So you have, I'm going to do it, yeah. So you have the rat population, this one here. You have your initial conditions. It oscillates because it's dependent on how many frogs there are. So they have competing sort of mechanisms. They have oscillations. And the frequency of this oscillation you can measure. It's also dependent on these variables in the equation. Kind of the p there and the p in front of this here. So just in summary, well, but basically there's also what's known as a predator and prey model. I'll look more stuff on Wikipedia. So today what I showed you in differential side of things, I showed how to solve them numerically, the very sort of generic way to do that. We saw how to solve with a constant rate, how to solve when you have a decreasing rate, so you have state dependent things, and when you have coupled populations, so these are oscillators. So these three ingredients are kind of important in all dynamics. They're always there, always happening. In these neural dynamics you have exponential decay, you have oscillations as well. Okay, now these look very, very simple, right? They look quite implausible. When you look at the literature, the equations look really, really crazy. But I'll tell you though, if we go back to that master equation we had before, we had dz dc equals f z u theta. This could be really nuts, okay? But if I was to plot that, z and f, if it looks something like this, let's just say, abstractly speaking, but if you kind of look at a small neighborhood of here, right, you can approximate this thing quite easily. So this isn't such a hideous thing. This ends up just being like a linear equation, much like the predator and prey system, for instance, or just a decay. So it depends on how, so this can be quite complicated, but if you're in a very small neighborhood, you can have dynamics that can be very, very simple, which is why I showed you the oscillations and this decay. They can all be in there. And in fact, what DCM does, it does something like this. It takes away a lot of these higher order, very complicated things and just focuses on very small, tiny parts of the full general system. This is what it does. Okay, so hopefully you kind of had some kind of experience now with differential equation. We'll talk about more of the next week. I thought you just about different types of ones. Now that you've seen some, you can think, okay, this is what this term means, this is what it means by negative, it means by decay, by oscillations. You can start to think mentally how they all look like. So for homework, to get you more your differential equations a bit better, so what I want you to do instead, I want you to do this on a computer. Don't try to do like the handbook stuff, but do the same type of algebra I had before, and I want you to solve this system. So the mosquito and frog system again. Okay. I had minus 0.1 times x, and I had y. Okay. So this is, because it's eaten by frogs. Now I'm going to include some state-dependent, on this state, activity. So I'm going to say the frogs are dying anyway at a rate of 0.5 times y. So use the same tools I gave you today. Write up some MATLAB code and show me next week how it looks like. Just a couple of things. Make delta t very small. Make it equal to like 0.1. Make y naught equal to 100. Make x naught equal to 0. So try. I mean, it took a little while just to get you to remind yourself, but I think it's just worth it. Just see how these models actually work. And you can also think of changing the parameters. how that influences your responses and how they look like. Just if you want to know about how to solve these things numerically. And hopefully it's fun. But you can tell me next week how it looks like, the response. And yeah, cool. All right, thank you for listening. I'm going to give you some reading material for next week. Essentially, it will be sections of that paper and a different paper. And then we'll kind of go from there and we'll show you the bilinear model itself. We'll go through the observation model, the hemodynamic model. And we'll go through what is a cross-spectral DCM. Essentially, what are the tools you need for that? And that will conclude kind of the generative model sort of stage of the tutorials. Cool, thanks. Someone should stop there. It's a red button.
見ればほどがいいですね。